Welcome to the video lecture on tornadoes, yet another thunderstorm hazard. Last time we looked at lightning, this time we're looking at tornadoes. Starting off with a quick definition, a tornado is a funnel-shaped, violently rotating column of air that extends from a thunderstorm cloud to the ground, and it can cause severe damage with its very high winds. That bit about being in contact with the ground is important because if it's just a funnel-shaped cloud coming down from a thunderstorm cloud and it's rotating but it's not making actual contact with the ground, we call that a funnel cloud. Funnel clouds can cause some problems too, but generally they don't do any damage at all. They dissipate fairly quickly. These tornadoes will come from the portion of the cloud that we call a wall cloud. This is a cylindrical cloud that protrudes from that base of that mesocyclone, and that's where that tornado is going to descend out of. Tornadoes form when warm, moist air near the surface meets cold, dry air higher up in the atmosphere, causing instability. Not surprisingly, they form in thunderstorms, hurricanes, and cold fronts. The difference in temperature and moisture between those two levels of the atmosphere can cause really strong updrafts that spin and they organize into like a rotating vortex. That would be that mesocyclone. If the conditions are right, these rotating updrafts can intensify and stretch downward to form an actual tornado. And this is just a really nice example of a wall cloud extending down from that larger thundercloud. This was taken near Little Rock in 2021. We didn't actually have any tornadoes develop from this storm. It just kind of did its thing and then it dissipated. But this is just a really nice example. What we're looking at here is a graphic of a tornado supercell. Remember that the supercell thunderstorms were our really big, violent storms. So a supercell thunderstorm contains a powerful rotating updraft, remember our mesocyclone. If that tornado forms, it will descend from that wall cloud, which is our cylindrical area, down towards the bottom of the cloud at the base of that mesocyclone. The picture at the bottom there, this is a tornado that formed from a supercell that was hovering over Campo, Colorado. So if we look at the spatiotemporal scale of tornadoes, these are considered mesoscale systems. They're, kind of middle of the road. They can vary in size and strength, but they're usually pretty short-lived. They only last maybe a few minutes. The average tornado lasts about 10 minutes, although some can be on the ground for a few seconds to up to an hour or longer. That is very, very rare, but it does happen. Supercell tornadoes tend to be longer lived, while those that are spawned like in your average squall lines and bow echoes, which we have not got into bow echoes, but these can only last for a few minutes. In terms of spatial extent, tornadoes typically have a path length of about 1 to 10 miles, but some can travel much further. The longest on-the-ground time ever recorded for a tornado was 3 hours and 10 minutes for a single tornado. This was set by the Tri-State Tornado of March 18, 1925 in the U.S. It also holds the record for the longest path, traveling 219 miles across Missouri, Illinois, and Indiana. Tornadoes are dangerous because of their strong winds and the destruction they can cause. Most of that destruction is due to flying debris. They can tear houses apart, but once those houses are torn apart and that stuff starts flying through the air, they can cause some even worse problems. So most of you are probably aware that with hurricanes, we have a ranking scale. We have category 1 through category 5. Hurricane Katrina, I believe when it made landfall, was a category 3, and Hurricane Harvey was a category 4, I believe. We also have a scale for ranking tornado severity. It's called the Enhanced Fujita Scale. This was developed by Dr. Ted Fujita of the University of Chicago in 1971. And then later on, they did add on to that based on a few other refinements, and it turned into the Enhanced Fujita Scale, or the EF scale for short. The Enhanced Fujita Scale ranks tornadoes from 0 to 5, so we have 6 different categories. This is not necessarily by wind speed, it's really ranked based on the amount of damage that tornado causes. An EF5 tornado is the most locally intense storm on the planet. We can have wind speeds of more than 200 miles an hour. This is spinning at 200 miles per hour. On average, we get about 1 per year in the United States. But bear in mind that that's an average. There have been a number of times when we have gone multiple successive years without a single EF5. And then occasionally we have years where we get a bunch. For instance, in April 3rd and 4th to be exact, of 1974, there were 148 total tornadoes across the U.S. on that one day. 7 of those were EF5s, and 23 of them were EF4s. It was a huge tornado outbreak. And here's our Enhanced Fujita Scale. You can see the 6 different tornado strength categories along with the damage that is associated at each level of strength. You can also see our estimated wind speeds. Basically what we're looking at is an EF0. Those wind speeds will be from 68 to 85 miles an hour, and they increase as you go up in rank, getting to our EF5, which is our highest rating. Those winds can be an estimated 200 miles or more. The photo you're looking at here shows some of the destruction from a May 4th, 2007 tornado that happened in Greensburg, Kansas. This was a bad one. Over 90% of the town was completely destroyed. In addition to destroying structures, EF5 tornadoes generate lethal airborne debris. I want you to think about it. If you've ever seen an old barn with that corrugated sheet metal for a roof, imagine one of those things tearing off and spinning through the air at 200 miles an hour. Not good. As an example of what we're talking about, look at this fork that is impaled in a tree. That took some force. If you look at our chart, notice that it says these wind speeds are estimated. That is because none of our instruments actually survive a tornado's internal wind speeds. So we don't know exactly how fast they are on the inside. If any of you have ever seen the original Twister, not Twister's the new one that came out recently, but the original Twister movie, I think it came out in the 1990s. The entirety of that movie's plot purpose is to try to get instruments inside a tornado to tell us about what's actually going on. That was a really long time ago, and this is still a problem because we still don't have any instrument that can really withstand the intensity of an EF5 tornado. So we have to pretty much guesstimate based on other evidence that we're seeing what those wind speeds are. Here, what you're looking at here is an aerial photo showing the damage done by an EF5 tornado that struck Moore, Oklahoma on May 20th, 2013. Fortunately, well, it doesn't look very fortunate here, but the tornado warning system that they had in place alerted people to find safety before that tornado struck, and at least kept the death toll to 23, which is still awful, but it could have been far, far worse. And unfortunately, Moore, Oklahoma is it's a tornado magnet. Just a few years later, they were hit by another one of these tornadoes. Same town. What we have here is a video that I unfortunately cannot show you over YouTube. If you were in class for this, you got to sit through this. This is a video of the April 27th, 2011 tornado that ripped through the Tuscaloosa, Birmingham area of Alabama. This one caused 64 fatalities. It was part of a larger outbreak of 367 tornadoes across the country on that same day. So listening to this, you are probably hoping, geez, I really, really hope that I don't live in a place where a tornado could ever hit. The problem is tornadoes can actually hit almost anywhere, and they have been known to do so pretty much everywhere except Antarctica. Now, in most places, it is very, very rare to get a tornado, but in some places they are much more prone to getting them, and they get them more frequently. For instance, lucky us, the United States has the most frequent and strongest tornadoes in the world, and poor Florida gets the most. The most active period for tornado activity is April through July, and if you had noticed with the tornadoes that I've cited so far, I think every single one of them was either in April or May. Spring through summer, about midsummer, is pretty much your big time for tornadoes. Geographically speaking, in the United States, our hotspot has traditionally been the Great Plains states. That's because in this area, especially at the time of year when we see those tornadoes forming, we have those warm, humid, maritime tropical air masses coming up from the Gulf of Mexico interacting with dry, cold, continental polar air masses sweeping down from Canada. We call this area Tornado Alley. Tornado Alley produces the strongest tornadoes in the world. As this tornado risk map shows, tornadoes occur on every continent except Antarctica, just like I said. The greatest frequency of tornadoes in the world, once again, occurs in the southwestern United States and the Great Plains states. The region of the Great Plains that extends roughly from North Texas to South Dakota is once again very often called Tornado Alley. When you hear somebody talking about Tornado Alley, that's what they mean. Now, if you look at the lower figure on this slide, this is showing you what's causing those tornadoes to form. We have warm maritime tropical air coming up from the Gulf of Mexico, dry continental tropical, remember that stuff that forms, that air mass that forms over Lake Mexico and moves up into the US. Dry continental tropical coming up from those interior deserts, and then we have our cold continental polar coming down from the north. Those all meet up in the Great Plains, and that is just the perfect recipe for tornado formation. These air masses often stack on top of one another, and together they provide a very high humidity, strong instability, and wind shear. And as we learned in the lecture on thunderstorms, that is the recipe for supercell thunderstorms, and those are our main contributors of tornadoes. Although remember that tornadoes also form in squall lines and in hurricanes. Here we have a map that's showing the mean number of tornado days per year. Notice we have our darker colors. These are the highest areas of activity, and we do have this whole section from basically Texas up through Kansas, Oklahoma, the Dakotas. That's very, very heavy. That is Tornado Alley. Note though, what's going on in the southeast, particularly over Louisiana and Mississippi and Alabama. We have equally heavy tornado activity. The tornado activity in this area has started to increase over the past, I'm going to say 10 years or so. So much more. It's kind of shifting from the Great Plains states towards the southeast in that particular area you see there, that it has earned this area now the name Dixie Alley. So we got Tornado Alley up in the Great Plains, and we have Dixie Alley down in the south. And I think, what have we had? Maybe 3 tornado warnings already this year, 2025, for Baton Rouge. So, yeah, it's getting bad here. If you remember back to that slide that I showed of Moore, Oklahoma, and I had said that the tornado warning system had alerted people ahead of time, and it had kept that death toll down to 23, which is actually remarkably low considering how bad that tornado was. A tornado warning system that alerts people to find safety before that tornado strikes has made such a difference, because our death toll and number of injuries from tornadoes used to be so much greater. So we have 2 levels of tornado warning system alerts. The first one is just a tornado watch. This is issued by the National Weather Service when the conditions are favorable for tornadic thunderstorm development. So we actually haven't seen a tornado yet. We just know that everything, the setup, the environment is perfect for a tornado to form. Those tornado watches get sent out, and people know to be waiting for the next level, which is a tornado warning. This is also issued by the National Weather Service after a tornado has actually been seen and called into the authorities, or is suggested by a Doppler radar hook echo signature. What the heck is that? Let's find out. But first, a quick look at annual tornado-related deaths. This is showing our tornado-related deaths per year, not injuries, from 1890 to 2017. Since the 1930s, as a general trend, tornado-related deaths, which are indicated by the blue bars, have decreased each year. And that red line you're seeing is just showing the long-term trend. Tornado fatalities have decreased even though populations have increased. And this contradiction is really explained by the development and the application of Doppler radar to provide earlier warnings to people in harm's way. I already told you about the year 2011 had an unusually high number of tornadoes and fatalities. Lots of them. The Joplin tornado in Missouri was particularly devastating, killing 158 people. The year 1925 stands out as the most deadly in U.S. history. That year had the single deadliest tornado in U.S. history, the Tri-State tornado, which killed nearly 700 people. Our death tolls and injuries are so much lower now that they have implemented these tornado warning alerts. And Doppler radar is primarily to thank for their ability to alert people to it. What you're looking at here is called a hook echo signature. If you look down in your lower left-hand corner, you see that little thing that looks like a J or maybe a seahorse tail curling out of that radar image there. What you're looking at is a Doppler radar reflectivity image. What it's showing here, that little J, is the hook echo signature produced by a tornado in May of 2007 in Greensburg, Kansas. The way this works is the heaviest precipitation on the radar map here is in orange and red. Pink indicates really large hail. Areas with no data are in black. That hook echo pattern, that J, is reflecting the rotation of the mesocyclone, not a tornado. Remember when we were talking about thunderstorms, I said that we can't actually see the mesocyclone doing its thing inside that thunderstorm cloud. But radar can. So the way radar works is it emits radio waves that bounce off precipitation particles like rain or flying debris. When these waves return, that radar analyzes their frequency shift, known as the Doppler shift, to measure the speed and direction of the particles. In a tornado, that rapidly rotating air causes really significant changes in the velocity of the particles, how fast they're moving and what direction they're moving in, which the radar can then identify as a strong rotation pattern. For hurricanes, the radar also detects the large-scale rotation of the storm, along with the distribution and intensity of rainfall. We'll learn about that some more when we get to hurricanes. But by analyzing these patterns, meteorologists can track severe weather, such as tornadoes or hurricanes, to issue these warnings and forecasts and really increase the probability of somebody surviving a tornado because they have time to seek shelter. So how much time do we have between when that tornado warning is issued and when the tornado itself actually touches ground? The answer is not a whole lot, but it's enough that it has significantly lessened the number of tornado-related fatalities and injuries over time. So that's good. See, the issue is that scientists can't actually predict which thunderstorms will spawn tornadoes. Yeah, they know what environmental factors to look at. They know when those conditions are just right that the thunderstorms could form tornadoes. But there's no guarantee that just because you have a supercell or a squall line, you're going to have tornadoes. So to help them narrow that down, they instead use that Doppler radar to look for key indicators like that hook echo signature that showed the rotation of the mesocyclone. These things occur before a tornado forms, and when they see that, they just make that call that they're going to send out that warning, because it's better to have a false alarm than not call it out. So that time between the warning issuance and when the tornado touches ground, we call tornado lead time. This lead time has improved markedly since they first started sending these warnings out, mainly due to improved technology and because we now have far more Doppler radar networks out there reporting, keeping an eye out and letting the other stations know as soon as they see something on radar. Our lead time has improved from about 5 minutes between warning issuance and the tornado touching ground in the 1980s to about 13 minutes today. And they are continually working towards increasing that lead time, because the longer you have for people to get to safety, the more likely they will survive the tornado. This graphic gives you some good tips on how to stay safe and sheltered during a tornado. First and foremost, if it is possible for you, quickly move to your basement if you have a basement. If you don't have a basement, try and find an interior room, not one of the rooms that's on an exterior wall. One that's inside, sheltered and buffered by those outer rooms. Get under a door jamb if that's all you have, because those tend to be built really well and they stand up well. They are structurally quite sound. Another option is getting into a bathtub, which is also surprisingly well built and structurally sound. Nice and solid. Do not stay in upper levels of your house if you have a house of multiple stories, because that top of your house is the first thing that's going to get ripped off when that tornado passes through. Once again, try not to go to exterior rooms if you can avoid it. Do not stand in front of windows. This is a recipe for death, because those windows will shatter and send glass flying everywhere. There is no place safe outside from a tornado. So if you have any option whatsoever for getting inside, even if it's not the optimum space, go inside. It's also a super good idea to have in those rooms that were areas I described that were pretty safe, like your basement, your bathroom, whatever, have some water just stored there, a working flashlight, and an emergency medical kit, because you never know when you might have to be stuck there for a while. Here we have some pretty motivating reasons for why you don't want to just stay in an exterior room of your house and you would like to find a more sheltered room, because debris that's being thrown around by the tornado can literally be blasted right through the walls of your house. And then finally, we're going to end with one more graphic telling you about tornadoes and road safety. First and foremost, try not to be on a road when a tornado is happening. Get off the road. Don't be there. Under an underpass is not a safe place to seek shelter. Nor is being in your car. We're not sheltering from lightning here. This is a tornado. A car is going to get picked up and thrown. So if at all possible, find some type of building for shelter and seek out those places that I said would be safest. That is it for this lecture. Our next lecture is going to be looking at mid-latitude cyclones. Stay safe and see you in the next video.